Hi, and welcome to my talk about systematic literature review search query refinement pipeline, incremental enrichment, and adaptation. This work was conducted at the University of New South Wales in Australia. I have no actual or potential conflict of interest in relation of this presentation. I'd like to thank CSIRO for funding my scholarships and UNSW for funding my participation at this conference. I'm a PhD student in computer science researching ways to improve systematic review process, especially the task of search query generation and refinement. Systematic literature reviews offer robust and transferable evidence for evaluating and interpreting research relevant to a topic of interest. Currently, performing SLRs is a profoundly methodical and time-consuming process. It requires the support of various researchers and contributors that play specific roles in producing SLRs. Furthermore, performing a review requires several time-consuming phases that's shown in the slide. Moreover, information overload in scientific publications obstructs the production of current and accurate SLRs. Therefore, conducting an SLR can become a huge endeavor that can often take several months to complete. My previous research has identified that defining the search criteria and queries is one of the most critical steps of a systematic review. Moreover, the quality and outcomes of a systematic review are ultimately decided by the search results. However, constructing search queries and conducting research takes significant resources and effort and prone to human error. The participant of our survey indicated this task as one of the most challenging of all. Building the search queries require extensive effort by experienced researchers who have high level of knowledge about the search system in digital libraries and research domains. Therefore, we have found that less experienced researchers, such as PhD students, face more challenges. Additionally, search queries development is not standardized, and there are currently multiple ways to construct them. On the other hand, our other studies showed that most of the focus of automation for systematic review is in the studies of screening and selection, and there's been very little attention to automation of the building of the search queries. Because of these findings, I started working on ways to automatically generate more effective search queries in order to help researchers when conducting systematic literature review search. To achieve this goal, we propose an incremental query building pipeline that is able to start from partially defined research questions or relevant paper abstracts as a set to construct a search query. It performs query enrichment and is adapting the search queries using the researcher's feedback by utilizing a probabilistic model in a reinforcement learning approach. Next, we go through each component of this pipeline. When the pipeline receives the seed, it performs usual text pre-processing and extracts the main terms of the seed, building a bag of words. When there are more than one seed available, it uses TF-IDF of the terms to select the most relevant terms. To build the initial search query, the pipeline uses an AND operator to concatenate the search term. The next step in the pipeline is the enrichment process. The objective of the enrichment is to make the query semantically enriched. We devise the pipeline with two enrichment approach. First, by adding the synonym sets of the terms in the initial query, and second, by using the word embedding approach. Finally, the first enriched query is built by concatenating the enriched search terms using an OR operation. The enriched query built in the previous step is passed to the digital library search engine using the library's APIs. It retrieves the search results. As you may know, the search result could contain hundreds of studies. To select the most relevant studies, we devise the pipeline with a sampling mechanism. Here, we use the board embedding approach. The sampling component ranks the retrieved papers based on their similarity to the initial set. In the next step, the high-ranked abstracts are presented to the researchers and they evaluate the relevance of the presented abstract by tagging them as relevant or irrelevant. In the next step, the pipeline extracts terms from both relevant and irrelevant abstracts that are tagged by the researchers. The pipeline uses this mechanism to promote or demote the terms that are already in the search query. If a search term appears in an abstract that is tagged as relevant, it will be promoted, while it will be demoted if it appears in an irrelevant abstract. The accumulated reward and demotes of the terms are used in the following step of the pipeline to delete a term or to replace a term in the search query with a more relevant term. To remove or add terms and to calculate the performance of the terms, we could use a heuristic model. However, this approach raises some questions for us, such as how many irrelevant papers should a term appear on to be considered as irrelevant and get removed by the pipeline. To overcome these concerns and this limitation, we frame the adaptating of the search query as a reinforcement learning approach in the form of a multi-arm banded problem, in which each term set of the search query is considered as an arm. We utilize a Thompson sampling algorithm for our banded problem. Cumulated rewards for each term is the number of relevant papers that terms appear on, and cumulated demotes for each term is the number of irrelevant papers that term appears on. At each iteration, an action is taken by adding or removing search terms to maximize the performance of the query in retrieving more relevant papers. In this slide, I'm showing a simplified example of the query adaptation process in 2 iterations. For example, in iteration I-1, we have 3 terms in the search query. The adaptation component observes new, relevant, and irrelevant abstract. In the next iteration, the probability value of the terms are recalculated. Therefore, we have a new term, term 6, that receives a higher probability to be more efficient in receiving and retrieving more relevant papers. Therefore, an action is taken by the algorithm and the less effective term is removed, which is term 3 in this example, and new term, term 6, is replacing that term in the query. In this slide, I'm presenting a real query of our experiment that is built in by the pipeline and get changes during some iterations of the adaptation process. As you can see, in the first iteration, we have some terms that I highlighted them as red because they're not performing well, meaning that they're appearing on many irrelevant papers. Therefore, the pipeline removed these terms and replacing them with more efficient terms, meaning that the terms that they appear on more relevant papers. We conducted several experiments to measure the performance of the proposed query generation and enrichment approach, as well as the performance of the proposed query adaptation approach. We performed the evaluation on SLO datasets that they were made publicly available by the authors. To identify these datasets, we looked for SLRs that had published their search and screening data. As a result, we identified 10 SLRs with different topics that were used in our experiment. In the first experiment, we assessed our approach in generating the search query directly from an initial seed by applying the query generation and enrichment components. To understand the impact of the amount of information in the seed on this component, we tested 3 different conditions: having only the research questions in seed, having the abstracts from 1 to 3 relevant papers, and the combination of these two. We only use the abstracts of the relevant papers as they capture a meaningful summary of the papers. In the second experiment, we evaluated the performance of the query adaptation based on author relevance feedback when incrementally refining the initial search query. To do so, we took the initial query generated with research question in the first experiment. Then we simulated the author feedback by leveraging the relevance assessment present in the SLR datasets. We assessed the changes in query performance within 5 iterations, where for the sampling method, we tested 2 different approaches, namely uncertainty sampling, where abstracts for feedback are drafted from those where the pipeline is less confident about the relevance, and certainty sampling, where the abstracts are drafted from those the pipeline is most certain about their relevance. The idea of these 2 methods was to test the impact of the class distribution ratio of the relevant to irrelevant papers in the author's feedback, since these contribute differently to the query adaptation. In summary, our evaluation showed that our approach is able to generate effective queries from high-level expressions of the scope of the review, such as research questions or relevant papers. The initial query generation and enrichment process is able to generate search queries that deliver 87.7% of the median recall of the manual approach, with only 24% of the result, meaning that the number of the items retrieved. While a solid approximation, we observe this process to be sensitive to the amount of the information provided in the seed and limited by the query enrichment method that might introduce non-semantically relevant terms to the query. On this, the proposed query adaptation is able to significantly improve on the initial generated query and achieve the performance of the original query in the course of 5 iterations with 5 relevant feedback each. Sampling methods, on the other hand, were shown to have a significant impact, with a sampling strategy biased toward positive examples found to be most effective. We demonstrated that our proposed approach is useful when limited information is available for starting an SLR search. We also determined that this approach can also be applied when some relevant studies are accessible to start the search. The main benefits are our proposed approach is that researchers do not need to construct initial Boolean queries. The approach can be implemented as an effective service, helping researchers to, at any stage of the SLR, to update a search query or initiate one. And the process is well suited for producing context for building search queries that are hard to construct. The reinforcement learning design of the pipeline makes it suitable for adaptation in any SLR topic. This would overcome the limitation that exists in previously proposed solutions. While this approach and its evaluation showed some initial promise in generating and adapting the search queries, there are limitations to the current pipeline and the evaluation methods. One limitation of the proposed enrichment approach is when the extracted terms from the seeds do not have many relevant terms in the embeddings. Therefore, selecting the most relevant terms becomes uncertain. Yet, replacing the general embedding models with a domain-specific embeddings model could improve query enrichment process. The other limitation in our proposed approach is that the pipeline only uses AND and OR operations for generating the Boolean queries. We'll leave exploring the impact of using NOT operation for generating and refining queries to future research. The other limitation of our experiment is regarding taking the SLR datasets as gold standard to measure the query performance. It is also required to measure the effectiveness of our proposed approach in building search queries that could retrieve relevant papers that are missing in the baseline SLR datasets. Finally, if you have any questions or interested in being involved in user studies that relate to this research, please reach out to me via email. Thank you.